September 1972, a Chevrolet-powered Vega rolling into the staging lanes at an NHRA national event, somewhere in the heart of the pro stock season. The temperature that afternoon was typical for late summer racing, warm enough that tire management and clutch heat were on every crew chief's mind before a single run had even been made. And behind the wheel of that Vega sat a man the entire pro stock garage had already learned, the hard way, not to underestimate. His name was Bill Jenkins. Everyone in drag racing simply called him Grumpy, a nickname earned honestly through years of exactly the kind of no-nonsense, get-out-of-my-way focus that separates competitors who are merely skilled from competitors who are genuinely obsessed. By that point in the 1972 season, Jenkins had done something that no engineer, no rival crew chief, and frankly, no physics textbook of the era fully explained to anyone's satisfaction. He had made 250 consecutive competitive runs across an entire season of national event and match race competition in a manually shifted 4-speed transmission without missing a single shift. Not one blown gear change, not one clutch failure that cost him a round. In a sport where the clutch and transmission were, for every other team on the property, the single most common point of catastrophic failure, Jenkins had built a car that simply did not break there, run after run, weekend after weekend for an entire season. NHRA technical inspectors, and more than a few rival engine builders who considered themselves every bit Jenkins's equal, pulled his transmission apart looking for the explanation. A reinforced case, an illegal internal ratio. Some kind of hardware nobody else had access to. What they found instead was a Chevrolet 4-speed manual transmission and a clutch assembly that was, on paper, built from components available to any competitor willing to source them. Nothing illegal, nothing that violated a single word of the Pro Stock rulebook. And that is the part that should genuinely unsettle you, because the reliability Jenkins was extracting from that combination simply should not have been possible using parts every other team in the class had equal access to. Here is the part that should disturb you even more. Jenkins himself, a formally trained mechanical engineer who had walked away from Cornell University because he found the actual work of building engines more compelling than sitting through lectures about it, was not hiding a single illegal part. He was hiding something the rulebook had no mechanism to regulate at all, a complete re-engineering of how a clutch, a flywheel, and a driver's own hand and foot were supposed to work together during the single most violent mechanical event in an entire quarter-mile run. Stay with me, because in the next 30 minutes I am going to take you inside the 5 specific engineering decisions behind what Jenkins and his crew called, with characteristic bluntness, the slick shift system. A complete rethinking of clutch and transmission technology that let Jenkins dump the clutch at engine speeds other teams considered a guaranteed way to destroy a driveline, and do it consistently enough to string together an entire unbroken season of competitive 4-speed racing. I am going to show you the actual mechanical reasoning behind each piece of it, not garage legend repeated without explanation for 5 decades. The actual metallurgy, the actual friction engineering, the actual driveline physics that turned a bone-stock-looking transmission into the most reliable 4-speed combination the sport had ever seen. And I am going to make you a promise right now. By the time this video ends, you will understand exactly why rival crew chiefs, men who had built championship-winning engines of their own, would watch Jenkins dump his clutch at revolutions per minute. They considered borderline reckless, and walk away not with an explanation, but with a grudging, speechless respect for a competitor who had apparently solved a problem the rest of the sport had simply decided was unsolvable. And the most uncomfortable part of that promise, NHRA never wrote a single rule specifically addressing what Jenkins had actually done, because nobody could isolate exactly which single component was responsible. Let's go back to where Jenkins started, with the flywheel everyone else assumed had already reached its limit. A heavier flywheel absorbed and smoothed out the violent torque spike of a hard clutch dump, protecting the transmission's internal gears and the rear axle from the kind of instantaneous shock loading that could shatter components in a fraction of a second. A lighter flywheel let the engine rev faster and recover RPM more quickly between shifts, but it transmitted far more of that shock directly into the driveline, which is precisely why most competitive teams accepted a heavier flywheel as the safer, more reliable choice, even at some cost to outright engine responsiveness. Jenkins, drawing directly on the mechanical engineering training he had begun at Cornell before walking away to pursue racing full-time, looked at that trade-off the way an engineer looks at any problem framed as a binary choice, by asking whether the binary itself was actually necessary. The sport-wide assumption treated flywheel mass as a single number that had to be chosen and lived with. Jenkins instead began experimenting with precise, selective machining of the flywheel's mass distribution, removing material from specific zones while concentrating remaining mass exactly where it did the most good for absorbing shock without sacrificing the engine's ability to recover speed quickly after each shift. The physics behind this modification comes down to how rotational inertia actually behaves. A flywheel does not need uniform mass across its entire disk to smooth out shock loading. It needs sufficient mass at the correct radius from the center of rotation to store and release rotational energy at exactly the moment the clutch engages, cushioning that instant without adding unnecessary total weight that would otherwise slow the engine's ability to rev freely between gears. Jenkins's modified flywheels behaved, in practice, like a component engineered specifically around the shock absorption problem rather than a generic, off-the-shelf compromise built for a broad range of applications it was never specifically tuned for. This single modification meant that when Jenkins dumped the clutch at RPM levels his competitors considered aggressive to the point of reckless, the actual shock transmitted through the driveline was measurably lower than what a conventional flywheel of similar total weight would have transmitted. That is the foundational reason his transmission survived 250 consecutive runs without failure. While other teams running nominally similar four-speed combinations were replacing gears, and occasionally entire transmission cases, multiple times across the same span of competition. NHRA inspectors weighing Jenkins's flywheel against class specifications found a component that fell within the legal weight range every single time. Because selective mass redistribution does not necessarily change total weight, only where that weight is concentrated within the disk. There was no rule addressing internal mass distribution, because nobody in the sport had yet demonstrated that this specific variable, rather than total weight alone, was where a meaningful competitive advantage could be found. But the reinforced flywheel only explains part of why Jenkins's driveline survived. The clutch disc itself had to be engineered just as carefully. The clutch disc, not a limitation. A four-speed clutch disc dumped aggressively at high engine speed generates an enormous concentrated burst of heat in the fraction of a second before the disc and flywheel lock together at matching rotational speeds. Every team in the sport understood this, and every team accepted a version of the same trade-off. A stronger, more aggressive clutch disc could transmit more torque, but it also tended to generate and hold more heat during that critical engagement moment, accelerating wear and increasing the odds of the disc glazing over or slipping in later rounds of competition. Jenkins approached this constraint the way his engineering background had trained him to approach any problem defined by an unwanted byproduct. Heat generated during clutch engagement was not a fixed cost of doing business. It was a specific, measurable engineering variable that could potentially be managed through disc construction itself, rather than simply endured. Working with his crew, Jenkins began experimenting with clutch disc friction material composition and internal construction, layering and selecting materials specifically to manage how quickly heat built up during the engagement moment and how efficiently that heat dissipated afterward, between rounds, rather than accumulating run after run the way conventional disc construction of the era tended to. This is closer to a materials science problem than a pure mechanical one. Different friction material compositions and different methods of bonding that material to the disk's underlying structure produce meaningfully different heat retention and dissipation characteristics, even when the disks appear externally similar and fall within the same legal diameter and configuration specifications. Jenkins's engineering background gave him a genuine advantage in reasoning through this problem systematically, rather than through the trial-and-error folklore that governed most competitors' approach to clutch disc selection at the time. The practical result was a clutch disc that could survive Jenkins's aggressive high RPM engagement style across far more competitive runs than a conventional disc construction would have tolerated, directly compounding the benefit of the reinforced flywheel discussed in the previous section. Where most teams treated clutch disc replacement as a routine, expected maintenance item across a race weekend, Jenkins's crew was replacing discs on a schedule closer to what other teams considered exceptional longevity, freeing up crew time and eliminating an entire category of the mechanical failures that regularly cost competing teams rounds or entire events when a clutch let go at the worst possible moment. Rival crews who examined a Jenkins clutch disc, on the rare occasions one was made available for inspection at a swap meet or after a private test session, frequently reported finding a component that looked, at a glance, unremarkable, consistent with legal friction material and standard construction methods. What they could not easily determine from a visual inspection alone was the precise internal bonding process and material layering Jenkins's crew had refined through years of controlled testing, data that existed only in Jenkins's own shop notes, rather than in any published specification sheet a competitor could simply order from a catalog. This is a recurring theme throughout this entire story. Nearly every individual piece of Jenkins's system, examined in isolation, appeared to fall within completely ordinary legal specifications. The advantage was never hiding inside an illegal part. It was hiding inside years of accumulated engineering data that competitors simply did not have access to and could not shortcut their way into recreating no matter how closely they studied the finished hardware sitting in front of them. We now come to the third piece of this combination, and it is the one that connects directly to the driving technique that made Jenkins's reputation as a four-speed specialist in the first place, about applying what he called slick shift technology in combination with slapper bar-style traction devices, a category of rear suspension hardware originally developed by other builders but refined and integrated by Jenkins's crew into a complete system, rather than treated as an isolated bolt-on component the way most competing teams approached it. A slapper bar, broadly speaking, is a rear suspension component designed to control wheel hop and axle wrap under hard acceleration, the violent, destructive oscillation that occurs when a car's rear axle attempts to rotate within the suspension under extreme torque, then springs back, then rotates again, in a rapid, damaging cycle that can destroy driveline components in seconds if left unmanaged. Every serious drag racing team of the era used some version of traction control hardware because uncontrolled axle wrap was catastrophic for reliability, not just an inconvenience. Where Jenkins's approach differed was in treating slapper bar geometry as directly integrated with clutch and flywheel engineering, rather than as a separate suspension problem solved independently. The specific stiffness, mounting angle, and engagement timing of the traction bars in Jenkins's cars were tuned specifically around the shock absorption characteristics of his modified flywheel and clutch disc combination, creating a complete system where each component's job was calibrated against what the other components were already handling, rather than each piece being over-engineered independently to survive worst-case scenarios in isolation. This integrated approach meant the total driveline, from clutch to rear axle, was absorbing and distributing the shock of an aggressive clutch dump more efficiently as a coordinated system than competing setups that treated flywheel, clutch, and suspension as three separate problems solved by three separate specialists who rarely compared notes. This is, in a real sense, systems engineering applied to a problem. The rest of the sport was still solving through component-by-component trial and error. Jenkins's Cornell training, even cut short, had exposed him to exactly this kind of integrated thinking, treating a mechanical system as a set of interdependent parts whose individual specifications only make sense in relation to each other, rather than a collection of independently optimized pieces bolted together and hoped to work well as a whole. There is a specific engineering insight embedded in this integrated approach that is worth spelling out clearly, because it explains why simply copying Jenkins's individual components, without understanding how they were calibrated against each other, consistently failed to reproduce his results. Consider what happens when a competing team, having heard rumors of Jenkins's success, sources a similarly mass-redistributed flywheel and bolts it into their own car without also revisiting their clutch disc construction and traction bar geometry. The lighter effective rotational mass at the flywheel center changes how quickly the engine recovers speed after a shift, which changes the timing and severity of the shock delivered to the clutch disc, which in turn changes how much heat that disc generates during engagement, which changes how much stress gets transmitted through to the rear axle and the slapper bars a fraction of a second later. Change one variable in that chain without adjusting the others, and you do not simply get a smaller version of Jenkins's advantage. You often get a worse outcome than the original, unmodified combination, because the new flywheel is now interacting with clutch and suspension hardware that was never calibrated to work with it. This is exactly what several competing crews reportedly experienced in the years immediately following Jenkins's dominant 1972 season, according to period accounts circulating through the Pro Stock Garage. Teams that attempted to reverse engineer isolated pieces of the slick shift system without access to the full integrated calibration Jenkins and his crew had developed through years of iterative testing sometimes found their own reliability getting worse rather than better. A frustrating and expensive lesson in exactly why an integrated engineering approach cannot be shortcut by copying individual parts in isolation. Word of these failed replication attempts only added to Jenkins's mystique within the garage, reinforcing the sense among rival builders that whatever he had actually built was more sophisticated and more resistant to simple copying than anyone outside his own shop fully understood. The fourth piece of this story is the one that turned all this careful engineering into something a driver actually had to execute, run after run, under the pressure of national event competition. The clutch dump technique. That redefined what aggressive meant. By Jenkins's own account, by the end of the 1972 season he was dumping the clutch at engine speeds around 6,000 RPM, at a time when most competing 4-speed drivers, working with 7-inch wide tires that the class rules restricted every team to at the time, were feathering the throttle and modulating clutch engagement far more conservatively precisely because their equipment could not survive and their tires could not effectively translate the kind of instantaneous power delivery a 6,000 RPM clutch dump represents. This is the point where every previous modification in this story converges into a single, repeatable action a driver has to physically execute. The mass-redistributed flywheel absorbed shock more efficiently. The engineered clutch disc managed heat more effectively across more runs. The integrated slapper bar geometry distributed the resulting torque through the driveline as a coordinated system rather than a chain of independently stressed parts. All of that engineering existed specifically to widen the window within which an aggressive clutch dump was survivable rather than catastrophic. But widening that window still required a driver willing and skilled enough to actually operate inside it consistently, without the hesitation or conservative feathering that every other team's equipment effectively demanded of its own driver. Jenkins's willingness to dump the clutch that aggressively was not recklessness. It was a direct, calculated consequence of trusting engineering he had personally overseen and validated through extensive testing, in a way that gave him a level of confidence in his own equipment that competing drivers, operating combinations built through looser, less integrated development processes, simply could not match. A driver who is not fully confident his clutch and driveline can survive an aggressive dump will, consciously or not, hold back, costing reaction time and early acceleration on every single run. Jenkins's 250 consecutive runs without a missed shift reflects not just mechanical reliability, but a driver who had eliminated the hesitation that was quietly costing every other team in the class a measurable amount of performance on every single launch. We arrive now at the fifth and final piece of this story, and it is the one that explains why, even decades later, rival competitors describe watching Jenkins's cars with something closer to professional bewilderment than casual observation. The engineering discipline that treated every component as part of one problem. Here is what separated Jenkins from nearly every other builder in the Pro Stock Garage during this era, and it is not any single modification described so far. It is the underlying discipline of treating the flywheel, the clutch disc, the traction bars, and the driver's own technique as four interdependent variables in a single engineering problem, rather than four separate components each optimized in isolation and hoped to work well together once assembled. Competing teams frequently had excellent flywheels, excellent clutch discs, and excellent traction hardware, sourced individually from whatever supplier or fabricator had the best individual reputation for that specific component. What they far more rarely had was a single engineering mind, trained specifically to think in terms of integrated systems, calibrating all four variables against each other from the very beginning of the design process, rather than assembling a car from a collection of independently excellent parts. This is precisely the kind of advantage that resists regulation, because it does not live inside any single component. NHRA's technical inspectors could isolate, measure, and compare against a rulebook specification. You cannot write a rule against a driveline being engineered as an integrated system rather than a collection of independent parts. You can only watch a competitor's car survive 250 consecutive runs without a missed shift, while understanding that whatever explains that reliability is distributed across four separate pieces of hardware and one driver's technique, in a combination that took years of iterative engineering discipline to develop and cannot be reverse engineered simply by copying any single piece of it in isolation. Here is what I want you to sit with after this video ends. Every modification described in this story, the selectively machined flywheel, the engineered clutch disc construction, the integrated slapper bar geometry, and the confident, aggressive clutch dump technique that all of it made survivable, existed entirely within what the Pro Stock rulebook of the early 1970s permitted. None of it required an illegal part. None of it required deceiving a technical inspector. What it required was a formally trained mechanical engineer willing to apply systems-level thinking to a problem. The rest of the sport was still solving one isolated component at a time, and the patience to develop that integrated system through years of careful, methodical testing rather than trial and error guesswork. Bill Jenkins built engines that powered 61 different NHRA Eliminator wins across his career, earned 5 NHRA Pro Stock championships and 3 AHRA titles as a builder, and won 13 NHRA national events personally as a driver, all while operating for the bulk of his driving career with a manually shifted 4-speed transmission. In an era when the rest of the sport was beginning to move toward clutchless planetary transmissions specifically because human-operated clutches were considered too unreliable to compete with consistently at the highest level, Jenkins made the supposedly obsolete technology work better, longer, and more reliably than anyone else in the sport, not through a single hidden trick, but through an engineering discipline that treated every component of a driveline as inseparable from every other component around it. He did not need a single illegal part to leave rival crew chiefs speechless in the staging lanes. He needed an engineering mind trained to see an entire system where everyone else in the sport was still seeing 4 separate, individually optimized parts. And in racing, in life, the competitors who understand how the pieces of a system actually depend on each other are very often the ones who leave everyone else wondering how something that looks so ordinary on paper could possibly perform the way it does on the racetrack. Consider what makes this story different from so many other legendary innovations in drag racing history. Most of the tricks this channel has documented over the years involve a single component, a flywheel machined a certain way, a fuel line routed next to a header, a chassis offset by a specific number of degrees, something an inspector could theoretically discover if they knew precisely where to look and precisely what to measure. Jenkins's slick shift system was different in kind, not just in degree. There was no single point of failure for a rival team to identify, no single component that, if copied precisely, would unlock the same reliability and performance. The advantage lived in the relationship between 4 separate systems calibrated against each other through a process that had taken years to refine, which meant that even a rival crew chief who correctly guessed at 3 of the 4 pieces would still fall short of replicating the whole, because the 4th piece, and the specific calibration connecting all 4 together, remained locked inside Jenkins's own notebooks and his own accumulated years of testing data. This is precisely why period competitors, men who were themselves exceptional engine builders and had no shortage of technical sophistication of their own, consistently described watching Jenkins's cars with a kind of professional frustration that went beyond ordinary competitive rivalry. Dino Don Nicholson, Ronnie Sox, and the other elite builders and drivers Jenkins raced against week after week throughout the early 1970s were not amateurs struggling to understand basic mechanical principles. They were, by any reasonable measure, among the most sophisticated engineers and drivers the sport had ever produced. And yet Jenkins's cars kept surviving longer, shifting more consistently, and launching harder than combinations built by people with equal or greater raw talent and equal access to the same catalog of available parts. That gap, sustained across an entire season and reinforced across multiple seasons that followed, is what actually explains the reputation Jenkins carried for the rest of his career. A builder who had found something the rest of the sport could sense but not quite name, one that extends well beyond drag racing itself. When a rulebook specifies individual components, weight limits, dimensional envelopes, material types, it inevitably leaves the relationships between those components almost entirely unregulated, because writing a rule against an integrated system requires the rule makers to first understand that such a system exists and matters, which in turn requires them to already know what a sophisticated competitor might eventually discover. Jenkins's engineering background gave him a structural advantage that had nothing to do with access to better raw materials or a bigger budget, and everything to do with a way of thinking about mechanical problems that the rulebook, written by officials focused on individual components rather than integrated systems, was simply not designed to anticipate or constrain. It is worth remembering, too, that Jenkins built this reputation during a specific window in the sport's history that made this kind of advantage possible in the first place. The Pro Stock category itself was created for the 1970 season specifically because match races between builders like Jenkins, Ronnie Sox, and Dino Don Nicholson had become so popular with spectators that NHRA recognized an entire audience hungry to watch exactly this kind of engineering rivalry play out on a national stage. Jenkins thrived in that environment precisely because it rewarded the kind of deep, patient, systems-level engineering he was naturally inclined toward. In an era before the sport's rules had matured to the point of anticipating and closing the specific kinds of integrated advantages, a formally trained engineer could still find hiding in plain sight. By the time NHRA and the rest of the pro stock field transitioned more broadly toward clutchless planetary transmissions later in the decade, much of what made Jenkins's specific four-speed advantage so significant became less relevant, not because anyone finally identified and banned a specific component, but because the entire mechanical category his advantage lived inside gradually fell out of competitive favor, replaced by transmission technology that removed the driver-operated clutch and the years of integrated engineering built around it from the equation almost entirely. This is a pattern that recurs throughout drag racing history, an advantage built with extraordinary patience and precision inside one specific mechanical category, only for the sport itself to eventually move past that category altogether, leaving the specific engineering that made a builder legendary as more historical achievement than ongoing competitive advantage. That transition did nothing to diminish what Jenkins had actually accomplished during the years it mattered most. 250 consecutive competitive runs without a single missed shift remains, by any measure, one of the most remarkable displays of mechanical reliability in the entire history of drag racing, achieved not through a single hidden component, but through the kind of integrated, systems-level engineering discipline that very few competitors in any era of the sport have ever fully matched. Jenkins earned the nickname Grumpy for his no-nonsense demeanor in the pits, but the deeper truth underneath that nickname was a competitor who had simply stopped accepting the trade-offs everyone else in the sport treated as fixed, and replaced them with a level of engineering patience that turned a supposedly obsolete four-speed transmission into the most reliable driveline combination the class had ever seen, right up until the moment the entire sport moved on to something else.